Hello, good morning. In today's video presentation, we shall be discussing about resultant of force system. Particularly, how are we going to compute for each magnitude? How are we going to compute for each direction? And at the end, or later part of this presentation, we shall have a sample problem that explains the process. Let's start with our discussion about resultant of force system. By definition, the effect of a force system is usually expressed in terms of its resultant, since the value of this resultant determines the motion of the body. So according to the discussion, the effect of the force system is usually expressed in terms of a single force, which is called resultant. And because this resultant will define the motion or tendency of the body to move, then the magnitude and direction of this motion is necessary to be known. And so how do we compute for the resultant of force system? So we will be reviewing the application of the parallelogram law as what we have discussed in our previous presentations about the actions of mechanics. Particularly, we will be dealing with the resultant of two forces when the two intersecting forces are perpendicular to one another. As an illustration, let us have this, two intersecting forces that are directed along the positive y and positive x-axis as indicated here by our illustration, that we have here F1 directed towards the positive y-axis and F sub 2 directed towards the positive x-axis. How are we going to compute for its resultant? According to parallelogram law, the resultant of these two forces shall be the diagonal of the parallelogram that will be formed by the vectors of these forces. And therefore it is necessary for us to create or to draw the parallelogram having these two forces as the sides. And now to do it, now let us imagine that we are at the tip of F sub 1. What we do is to draw a force parallel to F sub 2 and passing through that tip of F sub 1, and so we have this force. Afterwards, we try to look at this tip of F sub 2, and by drawing a force that is parallel to F sub 1, we shall have these forces. And now we have already done a parallelogram whose sides represent the magnitude of the two given intersecting forces. What is the resultant of these two forces? According to the parallelogram, it is the diagonal of the parallelogram that is formed by the vectors of these forces, and therefore this magnitude or this diagonal becomes the magnitude of the resultant of these forces. And looking at the parallelogram, you will notice that we have here formed a right triangle formed by this triangle. So with this triangle, we can compute for the magnitude of r using the Pythagorean theorem, such that the Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the square of the two other sides. Hence, r sub 1 is equal to, r sub 1 square is equal to f sub 1 square plus f sub 2 square. And therefore, r is equal to the square root of f sub 1 square plus f sub 2 square. What about if the two intersecting forces are not perpendicular to one another? As shown in this illustration, Let us imagine that we have here our f sub 1 intersected by another f sub 2 in this direction, such that the two intersect at a certain angle theta with respect to them. How do we get the resultant of these two forces? Again, we apply the parallelogram. And that is by drawing, okay, from the tip of the force f sub 2, a force parallel to f sub 1, and so you have that line. Similarly, at the tip of this f sub 1, we draw a force parallel to f sub 2, and that becomes our parallelogram whose sides having magnitudes equal to f sub 1 and f sub 2, and whose resultant shall be the diagonal of that parallelogram. Now looking at this parallelogram, you will notice that the angle that this side is making with respect to the horizontal is the same angle theta that the two forces are making with. And therefore, this angle becomes equal to 180 minus theta because this angle and that angle are supplementary. Now looking at this triangle form, what can you say about this triangle? You will notice that this triangle now consists of elements that are known, like two sides, f sub 1, and the sides representing the magnitude of f sub 2, and the included angle 180 minus theta. The third side represented here by r sub 1 is not known, and therefore this third side can be computed using cosine law. That is equal to r square equal to f sub 1 square plus f sub 2 square minus 2 times f sub 1 times f sub 2 times cosine of 180 minus theta. This is actually our definition of the cosine law, such that the square of the third side shall be equal to the sum of the square of the two sides minus twice the product of the two sides and the cosine of the angle between them. Now let us try to recall our definition of function of the sum of difference of two square, this cosine. According to our understanding in trigonometry, that the cosine of 180 minus theta is also equivalent to negative cosine of theta. So that if that would be simplified and then substituted in the first formula, then we shall have, okay, our formula for the computation of the resultant equal to r square equal to f sub 1 square plus f sub 2 square plus twice the product of f sub 1, f sub 2 times cosine of the angle theta. That gives you now the magnitude of r sub 2 or the resultant. In order to determine the direction of the resultant, let us imagine that we have here, okay, our initially drawn, okay, parallelogram, and from here we try to, okay, imagine the direction of the resultant. Okay, this angle beta that you are seeing is actually the angle that r is making with respect to f sub 1. And that if f sub 1 is horizontal, then this beta can now be used to describe the direction of the resultant of r, the magnitude of the resultant of r. And how do we compute for this angle beta? Now look at this, assuming that this is angle alpha, then looking at the triangle, we see that, okay, the triangle now consists of three known sides. So you have f sub 1, f sub 2, and r are already being computed, and one of the angle known, and therefore the other angles, beta and alpha, can be computed using sine law. So that, okay, r is to sine of 180 minus theta is equal to f sub 1 divided by sine of alpha, also equal to f sub 2 divided by sine of beta. Let us continue with our, okay, review of the parallelogram law. This time, in the resolution of force into components. According to the definition of a force, it says that a force can be resolved into an infinite number of combinations of components by the parallelogram method. Meaning, if you have a force, you can have it resolved into a different pairs of forces that represents its components. And so let us have this illustration. Assuming that we wanted to resolve the force into components that are mutually perpendicular to one another, meaning the two components are directed along two mutually perpendicular axes. And let us have this illustration. Imagine that we have here a force that is directed at this direction, and we wanted that this force be resolved along two mutually perpendicular axes, that is the x and the y axis. Meaning, if we know the direction of the angle, the direction of the cave F, then we can come up with a parallelogram by drawing lines from the tip of F parallel to x and y such that you have this K parallelogram. And the sides of the parallelogram represent the y component of F, while the side of the parallelogram represents the x component of F. And what we would like to do is to determine the x and y component of F, meaning the resolution of that F along the x and the y directions. Now looking at the illustration, you would see that you have here a right triangle such that the magnitude of F is known as well as the angle theta representing the direction of F measured from the positive x-axis. And because we have here a right triangle, using the function of right triangle, we can use Fy being equal to F sine of theta, whereas F sub x shall be equal to F cosine of theta. Now what about if the force shall be resolved into components that are mutually but not necessarily the horizontal and vertical axes? Take note, mutually but not necessarily the horizontal and vertical axes. So let us have here the illustration. Assuming that we have here our force F, and we wanted that this F be resolved into x and y, the two axes are perpendicular, but they are not necessarily the vertical and horizontal axes. It is very important that the direction of F with respect to either x or y must be known, such that this angle, assuming that this angle is the direction of F, that F is making with respect to the x-axis, and therefore what we do is to draw the parallelogram out of these forces. And how are we going to do it? Now to draw this, let us try to look at the tip of F. And from the tip of F, we try to draw a line parallel to the x-axis such that you have this direction, and another line parallel to the y-axis such that you have this direction, so that these sides of the parallelogram will represent the y component of F, and this side of the parallelogram shall be the x component of F. And again, because F shall be resolved between two perpendicular axes, then we will have here a right triangle formed upon illustration or upon drawing a parallelogram. This triangle becomes now a right triangle. And because that is a right triangle, then the two sides of the triangle representing the components of F can be computed using simple function of a right triangle such that F sub y shall be equal to F sine of theta, and F sub x shall be equal to F cosine of theta. Suppose we would like to resolve the force into components, but this time the two components are not perpendicular, meaning they are not at right angle. How are we going to do it? So to make an illustration, let us have here again a force that's directed in this direction. And let us imagine that this force shall be resolved along these two axes, along V and along W, which are not necessarily perpendicular. They are at a certain angle beta, which is more than 90 degrees. In this example, it is very, very important that the direction of F is measured either with respect to V or with respect to W. And assuming that that is measured with respect to V and the angle is equal to theta. Again, we shall be applying here the parallelogram law by drawing a parallelogram. So let us now try to concentrate looking at this F, the tip of F, and from there, we try to draw lines that are parallel to V and W, like this one. This line is parallel to V, and this line is parallel to W. And therefore, you have now drawn a parallelogram. Now, which of these parallelogram shall be the components of F along W and along V? So, you see this side becomes the V component of F, while this side becomes the W component of F, which can be computed using the principle of the parallelogram law. Do you see this triangle form? The red triangle form. Do you see this triangle? Now, in this triangle, what element of the triangles are known? If R is known and theta is known, then we need to know at least another element in order for the remaining elements to be computed. Now, I'd like you to look at this angle. Do you think we can compute for this angle? Yes, because if this angle is beta, look at this angle beta, then that angle shall also be equal to this angle. And if this angle is beta, this angle now, being a supplement with beta, can be computed as 180 minus beta. And then if that angle is already known, then going back to this triangle, you will now have here a triangle with at least two angles known and one side known. The remaining two sides and the remaining angles can be computed. Because this side or this angle can be computed using the concept that in a triangle, there are the interior angles of the sum of the interior angles of a triangle is equivalent to or is equal to 180. Therefore, that angle can be computed, assuming that angle is equal to alpha. Now, with the three interior angles of the triangle known, then the two remaining sides can be computed using the principle of sine law. And how do we write the principle of sine law? Sine law states that the ratio of the side to the sine of the opposite angle is proportional. Hence, we may write it as F is to the sine of the opposite angle, which is equal to 180 minus beta, shall be equal to Fw, which this one is to the sine of theta, the opposite angle, and also equal to Fb, which is this one, is the sine of angle alpha, which is the sine of the opposite angle. So from this equation, we can compute for the magnitudes of Fw and Fb representing the resultant of two forces along two non-perpendicular axes. Now, let us now try to determine how do we compute for the resultant of coplanar concurrent forces. So we're not already dealing with system of forces like forces that consist of more than two or more forces. First is that we have here a concurrent forces. When we say concurrent, meaning the forces are meeting at a common point. Imagine that we have here a force F sub 1 that is directed at that angle, theta sub 1, measured from the positive x-axis. And imagine that we also have another force F sub 2 whose direction is also defined in terms of an angle that it makes with respect to the positive x-axis. Assuming that we have another force here, F sub 3, and whose direction is defined by theta sub 3, that is measured from the negative x-axis. And we wanted to compute for the resultant of these three forces. These three forces are said to be concurrent because they are all meeting at a common point. And how do we compute for this? Okay, to compute for that, resultant is equal to the square root of rx squared plus ry squared. Now in this example, in this formula, how do we define rx? Now in this case, where rx is the summation of forces along x-axis. In other words, this is the summation of the components of forces along the x-axis and represented here by these forces. F sub 1 representing the x component of F sub 1. I have F sub 2, the x component of F sub 2, and F sub 3, the x component of F sub 3. Similarly, R sub y shall be equal to F summation of F sub y, or the summation of the components of forces along the y-axis. In the illustration, these are these forces. F sub y here represents the magnitude of the y component of F. This force, F sub 2y, represents the magnitude of the y component of the second force, and this force represents the y component of the third forces. In order for us to compute for the direction of the resultant, as it is also important that the direction shall be computed, because according to our discussion previously, the motion, okay, the direction or the resultant shall define the motion. If we expect, okay, that the object will move upon the application of the forces, then we have to define where will it be moving. In other words, what should be the direction of the resultant. The direction of the resultant can be computed in terms of an angle, theta sub x, which shall be measured with respect to the positive x-axis, and that is equal to r tangent r sub y over r sub x. So that is our discussion for, okay, the resultant of force system. Okay, we have defined how resultant can be computed using the parallelogram law, and in our, okay, presentation we have presented how the resultant can be computed, okay, using the formula. Thank you for listening. That's all for today.